All right, can y'all hear me okay?
Yeah.
Okay. So I want to spend a little bit of time talking about our next lab. So I'm probably going to have it do on a Sunday again. I just want to say a couple of things though before I start talking about the lab. I give you guys 2.5 weeks or so to do these labs. Part of the reason why is because they take some work. It takes some work to set up, and you're learning something new. And they're not cookbook type labs like you would like in a high school. Okay. Part of what I want you to do is to learn how to figure things out. And I had several students try to do the lab yesterday from scratch, and that ain't going to cut it. You're not going to be able to do these labs, especially in particular this one, if you're going to wait till the day of to do the lab. You're never going to make it. This one has so much data analysis error analysis that you'll never be able to do the write-up. So when the lab is presented, you should get started right away. If you have questions on the lab or something doesn't work, then we can figure out something to do to make it work. And it's your fault if you wait till 1 or 2 days before the lab is due to actually do the lab and then figure out something's not working. That's all on you, okay? Because we're online. Stuff we can do is limited online, and without your help, things won't get done. So I can do whatever to help you, but you got to help yourself. So some of you guys waited so long to do the lab, and I got things like I can't figure it out. Well, that's why I gave you 2.5 weeks to do the lab. Okay, so a lot of this is on you guys. If you can't do the lab right away, if you don't start the lab right away, it's on you that you didn't get it done. Okay. So anyway, I had to say that because I was upset with a couple of students. So after having said that, tell me about issues you had carrying out the experiment. I mean, I know one of the issues was the bulb.
Works fine for me, actually. I didn't really have any issues.
Okay. Because, you didn't have alligator clips or you didn't have any clips to clip to the bulb, right?
Yeah, that would have made it a lot easier, but other than that,
okay.
Like Andrew said, it was pretty straightforward.
And of course, not having the diode didn't help either, but okay. Because some people had issues with the light blinking. That's part of not having a good contact. And I'm concerned too as to how well regulated that power supply is, or how close we are to the max. The rating, it says 2 amps max, but I always worry about the total power, although it says 30 watts. I just worry about when you reach the max on these things, regarding how well regulated they are, etc. So, okay, so it worked okay for you guys. So our next lab, you're going to be using that breadboard again, and you're going to be wiring circuits that we actually discussed in class. I actually solved one of the circuits in class. So this is the circuit you're going to be looking at. Remember I did the Wheatstone bridge problem, and then I put an ammeter across those two points of the Wheatstone bridge. So that's what we're going to be looking at in this lab. So in the first part, you're going to hook up on the proto board this circuit. And again, let me just show you, because I wired it up. I can show you what I did. It's kind of small though. In fact, what I did was I used tape to tape the connector for the adapter. Okay. because otherwise things fall out. So I did something like this. You can do whatever you want, but I wired this circuit up on the proto board. You're going to have to use an ohm meter to measure the resistance of the resistors. Remember that everything we're doing is following, really follows the stuff that you should have learned in the multimeter quiz. And if you didn't quite understand something in the multimeter quiz, then you got to come and talk to me, okay? Because it's going to get more sophisticated as we go on. And in this lab, one of the things I want you to do is you're going to take a picture of your circuit and you're going to copy and paste it into your lab report. So ideally, what I would like for you to do is to measure currents, but it's a pain to measure the currents with this printed circuit board. It's also easy to make mistakes and blow a fuse. So what we're going to be doing is in the circuit, we're going to be measuring, hold on a second. We're going to be measuring voltages across the resistors. And we're going to take the voltage drop across the resistor and we're going to divide it by the resistance value, and you're going to determine the current. So basically, you're going to measure the resistance values. I mean, we're not going to go by the color code. You'll measure the resistance values, and you'll measure the voltages, and then you'll calculate the currents. And so what we're going to look at is Kirchhoff's current rule. So you have this circuit. And you're going to measure the voltage across this guy and divide by the resistance, this guy, divide by the resistance, etc. So you can get the current here, and you can get the current here. Where's that current coming from? It's coming from this. So this is the current through the source. And if you apply the loop, the current rule, or the current rule, you can see that I sub s is IR1 plus IR4. So you want to see if this is true. And then over here, you're going to have a current going this way, and you're going to have a current going this way. This is IR3, IR4. And again, using the current rule, I, the source, is going to be IR3 plus IR4. So you want to check this. Okay? Yeah.
Do you mean IR1 plus IR2 on top?
2, yes. I don't know why I was thinking 4. Thank you. Are we okay with that? Now, here's the thing. We're going to do some error propagation. If you notice in that table, it wants R plus the uncertainty in R. So if I take one of these resistors, and I take any one of them, like this guy right here, they're tiny, right? And it measures resistance. What's the uncertainty in the resistance? By the way, for me, because I don't have alligator clips, if I wanted to measure the resistance of this guy, I would put this in the proto board and put the leads on either side of the resistor to measure it, because then I can get a good contact between the lead and the resistor. Because if I hold it in my hand, that's going to be hard to get a nice, good, consistent contact. Okay? It's up to you, but you'll notice a difference. But how do I get the uncertainty? Right? How do I get R plus or minus delta R? How do I determine this value? And you don't have to measure it like 12 times and to get the uncertainty. Okay? These multimeters, by the way, to measure current, I did this last night, to measure current, I took some, I don't know if you can see this. I actually taped some wires to the leads so I could actually measure current, because I didn't have alligator clips. Or actually, I wanted to simulate what happens if I don't have alligator clips. So I actually taped some wires to the meter lead so I can measure current. But I'm going to take these off now. So I want to measure the resistance. And really what I would do is look at what decimal place, to what decimal place does this vary? All right? This thing will give me a whole bunch of decimal places. Oops, hold on a second. For some reason, it's not working. Somehow my multimeter is not working right now. Okay, so this will give me something to the 100th place, for example. If it varies to the 10th place, then your error is to the 10th place. So you basically, basically determine the resistor reading based on to what decimal place do I see the variation. I ask myself, to what decimal place do I see a variation in the meter reading? Okay. Same thing, if I measure a voltage, to what decimal place do I see the variation? So when you're doing this lab, I prefer, I would prefer, and I didn't really, I didn't see some of the numbers very well, but you actually with this cheaper one, you can get some decent results with it, but this one's a little bit better. I prefer to use this to measure this current. You're going to put the meter, you're actually going to measure this. You're going to measure this current. That's the only direct measurement you'll be using, and everything else is calculated. But anyway, I prefer to use this to measure current. So you just got to ask yourself whether you measure a current, a resistance, or a voltage. To what decimal place does the meter reading change or vary? Okay. And now I'll give you the uncertainty. So it's an estimate, okay? Instead of having you measure something over and over again, which will become tedious. So you'll know R plus delta R, and you'll know V plus or minus delta V. And you're going to calculate I Really, these should be deltas. Well, there's too many deltas anyway. How do you find the uncertainty? If this is calculated, how do I find the uncertainty in this? You go back and do error propagation, just like you did in Physics 205. Okay. You're going to be using the same ideas as in Physics 205. Nothing's changing. All right. So you'll be doing a lot of this. So in this table, that third column, you want I and delta I. So you're going to have to do that calculation for delta I 4 times. I do expect you to show your work. Okay, because I need to know what numbers you put into your equations. I don't want to just see the equation. I need to see the numbers that you put in the equation. Because otherwise, how do I know that you know what you're doing? Okay. Now, you don't have to show, when you're doing I plus or minus delta I, you don't have to show the calculation 4 times. You just show it once. That tells me, you know, as long as you did it correctly, it tells me you know what you're doing. Obviously, if you did that one calculation wrong, it's possible you'll have all 4 calculations wrong. Okay. But you know, when I say to show your work, don't show your work for every single calculation. Show it for one, and I'm going to assume you did the rest the same way. Does that make sense? And if Professor Shakel says, you wouldn't have to show your work if nobody in the class made a mistake. Okay. So the first part, you're verifying, you're trying to verify the current rule. And then there's some questions for you to answer. Do your results verify Kirchhoff's voltage law? In other words, if you measure the voltage drops across this loop, it doesn't have to be this loop. You can choose a simple loop. There's 4 resistors here. Does the sum of the 4 voltage drops in this loop add up to 0? Oops, let me go back a little bit. Do the sum of the voltage drops add up to 0? Okay. Or you can choose this loop, this outer one, with the power supply R1 and R3, or the power supply R2 and R4. Choose a loop and see if it obeys Kirchhoff's voltage rule. And it does take time to do this live. It's not that quick. Okay, just because of the questions you have, etc. Questions so far? And if you have trouble, I need to know where you're getting stuck. So you get started right away, then we can figure out what's going wrong. This one should have less problems than the previous one because, you know, there's not that many parts to it. There's 4 resistors, your 2 meters, and the adapter. You'll set the adapter to 6 volts. And you'll hook up the circuit here. Remember the proto board is just basically a substitute for wiring things with clamps or with electrical tape. Then part 2, let me go to part 2, sorry. Part 2, the difference is it's really the same circuit, except this time you're going to have you're going to have an ammeter between points A and C. Okay? You'll have an ammeter between points A and C. You want to measure how much current goes through through that ammeter. Of course, when you put the ammeter there, now points A and C are essentially the same potential. This circuit's different from the one in part 1 because you put the ammeter in that place. So what I would do, I'll show you what I would do. On this board, and you also have to have that meter in place. I think I took out one of my resistors. And I forgot to put it back. And I lost my resistor. Anyway, oh, here it is. Let me put my resistor back in place. So I put these 2 wires that are sticking up. I would connect these to the multimeter. In fact, what I would do is bend them over like this and tape the multimeter, the good one, to these. Tape the leads to these. This is what I had done before, okay. And then that's always going to be in the circuit for all the other measurements. And so that current shouldn't change as you do the measurements. So you'll have the good meter, the better meter, I should say, measuring the current. And then the other meter, you'll be measuring the voltages across the resistor. Okay? You'll use the other meter to measure the voltage across the resistor. Questions? So,
I'll think of something.
okay. So you'll have the meter.
Right now, sorry.
You'll have the meter right here. It's got to be there the whole time, even when you're measuring these. When you're measuring the voltages. I'll leave that there. So some of the current will either go this way or that way. It doesn't matter. So I'll call this IAC. So you're always going to be measuring this. This has to be there the whole time you're measuring these voltages. Because if you take that out, you're changing your circuit. Because when you hook this together, if the meter resistance is low enough, then these 2 points will be at the same voltage. Go over the example I did in class. Because I did this example in class. If you don't remember, go watch the videos. It was about a week ago. So then this current is going to depend on this current and this current. Based on the way I wrote it, that's what IAC is going to be. And it's either going to go this way or that way, but you have to figure that out. Okay? It's possible, it could go either way. I just wrote it this way, but it depends on the resistor combinations I have. Make sure that when you set up your circuit, if you make it look like your picture in the lab, make this the positive side, this the negative side, okay? Hook the positive side of the power supply here and the negative side of the power supply there. How do you figure that out, by the way? How do you know which side's positive, which side's negative on your power supply?
It says so.
Well, let's say it didn't say so. Let's pretend it didn't say so.
Well, you just see whether the voltage across is positive or negative.
Yeah, if I use this meter, if I hook up positive to negative, if I hook up the positive of this guy to the negative of the power supply, the voltage will be negative. Okay? Again, what I'm trying to get you guys to do is think about what you're doing. These are not cookbook labs. Okay, you need to do some learning. It's not just following a bunch of, tell me what to do. Because some people think the labs are basically someone's telling them what to do and they do it. And that's not what we're trying to teach you at Sierra College. Okay. All right, so then you're going to calculate this. And of course, what's the uncertainty in this thing, right? We have to use error propagation. So there's a lot of error propagation calculations in this lab. There's a lot of them. Then the last part is really the same circuit. The only difference, you're going to make the same measurements.
So, Professor?
Yes.
So the error propagation, we only propagate whenever we're doing the percent difference, right? That's the only time we need to.
I'm not sure I understand that question.
Like from part one, like when you're doing calculating the percent difference from the Kirchhoff's calculation.
Oh, here.
That would be the only time you need to propagate, right?
Well, if you look at this, hold on a second. Let me change to the full screen here. All right, you're propagating errors in column 3 of table 1.
Oh, so we're actually calculating those values. Okay.
Yeah, you're calculating your uncertainties using error propagation. Okay, this down here is what you measured. Okay, this is what you measured with the ammeter. And then the calculated I sub s along with his uncertainty, that's error propagation. Anytime you see the word uncertainty, that means error propagation. Anytime you see the delta symbol, that means error propagation. Does that make sense?
So would we have an uncertainty in our percent difference as well?
No.
Okay.
Yeah, you never did you never did that last semester, right?
Can't remember.
Okay.
I don't think so.
No, yeah, you don't do that. So basically the percent difference is going to, you're going to use the rules for sig figs. So if you get 1 sig fig in this value, that means you have a good percent difference. If you have 2 or 3, that means your results are bad. Well, I mean, I got to be careful when I say that, but generally that's the case. If everything's to 2 decimal places and your percent difference is 2 decimal places, you're probably above 10%. Does that make sense?
Yeah.
Okay, all right. So yeah, third column will be, you'll be doing error propagation. This value requires error propagation. Okay. All right. So you notice there's, in part 2, there's 2 sets of tables. And what you're going to do in this table 3 is you're going to change the scale setting of the ammeter to something that goes to maybe, that has a higher resistance. Because I want you to see the effect of having a higher resistance in measuring current. So in part 2, you're going to do this twice. Once with a scale reading that has a low resistance, and it'll probably be the 200 milliamp scale. You can't do the 10 amp scale, it's too. When I did the measurement last night, the current was low. I don't think you can do the 10 amp scale. You can try it. Okay. So let's say you do the 200 milliamp scale and the 20 milliamp scale. Do you see any differences? If you can do the 10 amp scale, that'd be great, because the resistance of the meter on the 10 amp scale is so low. But the resistor values that were chosen doesn't allow a large enough current through here. You can start at 10 amp, and then when you do table 3, you'll do the next lowest scale. Does that make sense? And the idea is to show you the effect of the resistance of the meter on your circuit. Okay. When you get to the, I forget what it was, the 2 milliamp scale, the resistance is significant. Just be careful. This is one of those labs where you can blow a fuse, so you got to do it right. I had one person who didn't have the meter wasn't working, so I couldn't figure out what was wrong with it. I'm not sure if you turn on the meter and it's blank, the first thing I would look at is a contact with a battery or a bad battery. If you're measuring current or voltage and it always reads 0, that tells me you have a bad fuse. Now, all the meters that you got come with instructions. And usually instructions have troubleshooting guide. And this one might not have the best troubleshooting guide, but you got to read the instructions. Okay? Inside the box, there's a set of instructions. You got to read them. Okay, that's part of becoming an engineer, is learning how to read instructions. And when you take Pattingale's classes for engineering, he will make sure that you will read instruction manuals. Okay. All right. So really, that's the essence of the lab. It's not, in terms of technique, it's not super complicated. Again, it's learning how to wire circuits. And you need to get started as soon as you can. So if there's trouble, then you can communicate with me. We can set up a Zoom meeting. I can have you maybe have Tyler, maybe communicate with Tyler regarding the equipment. Maybe you need a new piece of equipment. But if you wait till the last second, that's kind of your fault. You waited too long. You won't be able to do it. Okay. We're online, you know, we can't, the class can't be treated the same way as when it's on ground.
It's due in 2 weeks?
Yeah, I'm going to make it due to 25th, which is
It's a Sunday.
It's a Sunday, yeah. So I'll make it due on, so it's a little over 2 weeks. Okay.
And the exam is this Friday, right?
The exam is this Friday. So, any questions? Because then the next thing is I'll talk about the homework.
Actually, I do have one question.
Okay.
So this current homework, is this on exam material as well?
Yes, this is chapter 28
Okay.
homework, right?
Okay.
Yeah, the
I thought
exam
so.
is on chapters 26, 27, and 28.
All right.
Oh, one more. So I just realized one more thing. There's a derivation you have to do in question number 6 in part 2. It says derive an expression for the current through R1 when the ammeter, assuming an ideal ammeter, is connected between points A and C. So I expect you to use Microsoft Word's equation editor. Or if you have math type, use math type.
We use like, as long as it like looks good, like, cause I use like code cogs, if you know what that is.
As long as it's typed, it's not handwritten,
Okay, yeah.
right? I don't want handwritten equations. You lose points. If you change format on your lab, you lose points. Okay? I want it, however you use, you know, some people might use OpenOffice, or not OpenOffice, what's it called now? I think it's called Libre. And it has its own equation editor. Use some sort of equation editor. It's got to be typed. Okay. And let's see, before I forget. Yeah, this whole document, I want typed here. You see where it says paste your picture here? That's the picture of your circuit. I want you to put it there. With the, show the meters too. Don't just show the breadboard. or the proto board, sorry. Okay, show where your meters are at and everything. So that it looks like, it shows me that you know what you're doing. No other questions? Okay. So, let me switch to a different window here. We go to WebAssign. Oops. So basically every exam really covers, at least in this course, every exam covers 3 homework assignments. So questions on the homework?
Not yet. I'll probably have some in office hour.
Okay. So tomorrow, my office hours will be from 2 to 3. I had to move them. Okay?
Sounds good.
I'll type it on the chat just to make sure. Okay. Anybody have questions? And I'll be keeping an eye on the Discord too.
I have a question on 14 on part F.
Okay. So you want to determine the current through switch S2 after, one time constant after the switch is closed. Okay. And let me make sure, switch S1 is closed also. Okay, so the capacitor is going to discharge, right?
Yeah.
Okay. Just give me a second, get my red notes. And you're still going to have current running through R1.
Right, because that switch is closed. That's one.
Yeah. So you got to consider the capacitor is going to be discharging. And so going through S2, you're going to have current coming from R1, and then you're going to have, if you look at this junction, I don't know if you can see that it's kind of small. Let me blow up the picture. So you're going to have current coming from R1, and then current going from because of the discharging capacitor. Because this is going to be closed. Once you close this is going to have a path, all right? So it's going to be 10 over whatever R1 is. That's going to be the current through here. Because when you close a switch, this point and this point, then they're at the same potential. Right?
Oh, yeah.
Okay. So then you got to consider that one current coming this way, and another current going through because of this guy. Does that make sense? So
Yeah.
you got to use the Kirchhoff's current rule.
Yeah, that makes sense.
Okay, all right. And again, how many times are you going to use the equations for charging and discharging a capacitor? You're not going to use it that many times in this problem. I think part G you use it. I think really that's it. This is probably the hard problem on the assignment. I think number 15 is, this is just an RC circuit. Just combine the two capacitors, combine the two resistors, and it's not that bad. This looks like a problem I did in class. So you should be able to do this one because I essentially did this one in class. This one, just remember when the capacitor is fully charged, right? You can figure out the voltage drop between this point, between this point and this point. When the capacitor is fully charged, all the current goes this way, and all the current goes this way. It's basically like part 1 of the lab. And so all the current goes through here. So these two resistors are in series, these two resistors are in series, but this combination here is in parallel with this combination. So once you figure out the current through here and through here, you can get the voltage drop here and the voltage drop here. And then you can find the potential difference across the capacitor.
Hey, Professor.
Yeah.
So for part, well, C, so the charge would be 0 only when the left and right resistance are the same? Or is it when, well, because you can't, well, because the potential, there'd always be a potential across the capacitor with this configuration, wouldn't there?
If, depending on the value of R, right? If you have a balanced Wheatstone bridge, then the charge in the capacitor can be 0. If you have a balanced bridge, which means that the potential here and the potential here is the same.
Would that be impossible in this case?
Yeah, in this particular case, what is R? Yeah, you know, this question.
Well, for the answer is yes, that it can be 0, and that's why I was confused, because it's like, it doesn't seem like it, because there's, at that junction, there's always a potential difference.
Yeah, I think what they're asking for, if we don't know what R is, if R can be any value, can the charge in the capacitor be 0? If that's the question. If R can have any value, not the 24.1 that you see on the screen. It's kind of misleading the way they ask the question. Does that make sense?
Well, yeah, but at what case would that be true? That's what I'm trying to like understand.
Well, remember the Wheatstone bridge I did in class?
Yeah.
So in the Wheatstone bridge, we set the condition that the ratio of the top resistor to the bottom resistor has to be equal to the ratio of this top resistor to the bottom resistor.
Okay. I see how this is, okay.
And what that means is that the potential drop across the capacitor is 0. So this point, I don't know if you can see me doing this. The point to the left of the capacitor and the point to the right of the capacitor are at the same voltage. Then that means the voltage drop across the 3 ohm resistor and the voltage drop across a 2 ohm resistor are exactly the same. That's what that means.
Yeah, I see it now. I get it. Yeah.
Okay. Yeah, I mean, when you look at the question, they tell you, they give a specific resistance, and then they ask you that question. That to me is out of order. They should ask C before they ask B. At least that's what I think. By the way, if for this kind of thing, if you just type yes or whatever, it should mark it correct. For the where it says explain your answer, just type anything in there. Are there questions? Or concerns? So don't forget there's a set of unit conceptual questions for this unit, and then again the answer key is at the bottom of the modules page. So you might want to go through them too to help you study for the exam. I don't know if you've noticed, I try to be more conceptual and mathematical on exams. So this test I will have 4 problems. It's not, choose the ones you want me to. Basically, on the second and the fourth exam, I just give you a certain number of problems to do. On the first and third, because they're usually harder units, I give you I give you choices. So on the third exam, you'll see I'll give you 5 questions, and you got to do 4 of them. But I won't do this on exam 2. Are we okay?
I'm all good.
Anybody else have any questions or concerns? So you have a lot to do between now and Friday. Just finish this assignment. Get ready for the exam. Then start in the lab. Start in the lab as soon as you can. I know you want to study for the exam first. That's fine, but just don't wait till the day the lab is due. That was, getting questions like that on the day the lab is due. That's not good. Okay. So if you have any questions, just email me or come to my hours. I have one today from 1 to 2. And as you get started in the lab, if questions come up, then I can see what issues students are having issues with. And we can go on from there. But I don't foresee, other than students having trouble wiring the circuit, I don't see a lot of technical issues on this lab. Okay, I guess that's it then. Nobody has questions. I'll end it here. Are we okay?
All good.
Okay. So everybody's quiet. Okay. We'll see you on Friday. Or earlier if you have questions.
See you later today.
Okay. Oh, yeah. Okay.
Yeah.
Okay.